So now let's solve an example problem. Two solid cylindrical rods AB and BC are welded together at B and loaded as shown. Determine the magnitude of the force P for which the tensile stress in rod AB has the same magnitude as the compressive stress in rod BC. We're also given a picture with the word problem, so it's easier to visualize. But before we begin solving for anything, let's use the given find solution format to determine what information we're given and what we need to solve for. So we're given the diameters of each of the rods. The diameter of rod AB is 1.25 inches, and the diameter of rod BC is 0.75 inches. We can also see from the picture that there's an external force acting at B, and that's 12 kips, or kilopounds. And finally, we're given the lengths of each of the rods. Rod AB is 30 inches long, and rod BC is 25 inches long. We also need to find P, for which the normal stress in rod AB is equal to the normal stress in rod BC. We'll go ahead and make the problem a little smaller so that we have more workspace. As you can see, the following solution is labeled number 1, so there must be a number 2. We'll be going over both approaches to this problem very soon. So our first step is to draw the free body diagram of the rods. We have to make sure to include the dimensions of the rods as well as all of the forces acting on them. We have the lengths, the diameters, and the forces at points A, B, and C. You can see that I replaced the support at point A with a normal force labeled N sub A, which is the force that the support exerts on the rods. Here, I have the arrow pointing upwards to indicate that I'm assuming the normal force acts in that direction. You can choose to draw the arrow downward, but just make sure to account for that when you decide which direction will be positive and which will be negative in your equations. If your assumption is right, then you'll get a positive number. And if you get a negative number, that just means that the normal force was actually acting in the opposite direction. Our next step is to find the internal forces in each of the rods. Remember, both statics and mechanics of materials are highly dependent on the three main equations of equilibrium. Before we find the stress, we're going to need the equations to find the internal loadings first. Here, we're going to use the method of sections to do that. We've sectioned rod AB to find the internal resultant force labeled F that counteracts the normal force at A. I chose the most common directional system in which up is positive and down is negative for the force vectors. The equation of equilibrium we'll be using here is the summation of the forces in the y direction, which should be equal to 0 because the system is, of course, in equilibrium since it's not moving. N sub A acts upward, so it's assumed to be positive in the second line of my solution, and F acts downward, so it's negative and is subtracted from N sub A. Once we simplify that, we can see that the internal resultant force F is equal to the external normal force N sub A. We're going to do the same thing to find the internal resultant force in rod BC. To do that, we'll need to section the whole system at some point between points B and C, and consider all the forces that act on either the top section of the system or the bottom section. We'll take the top section. Again, the sum of the forces in the y direction should equal 0. We have three forces altogether: N sub A, the 12 kip force, and the internal resultant force. Here, we've labeled the internal resultant force as P. Think about why we did that. What would have happened if we considered the bottom section of the system instead? The internal resultant force would have had to equal the external force P acting at point C. So we know that the internal resultant force must be equal to P. That's why we labeled it P in the free body diagram here. Now let's simplify. N sub A points upward, so it's positive. The 12 kip force points downward, so it's subtracted. And P is assumed to act downward, so it's subtracted too. If we rearrange the variables, we find that P equals the normal force minus 12. Remember what we're trying to find. We need the value of the force P for which the stresses in both rods are equal to each other. The equation of stress is internal force over cross-sectional area. From the last slide, we saw that the internal force in rod AB is equal to N sub A, and the internal force in rod BC is equal to N sub A minus 12. Now let's find the cross-sectional areas. These are solid cylinders, so if we cut them perpendicular to their longitudinal axes, the cross-section should be a circle. The area of a circle is pi r squared, but we're given the diameters of the rods instead. So we'll use pi over 4 times the diameter squared, and you can see the calculations for how we derived it on the screen. We wrote in our list of givens that the diameter of rod AB is 1.25 inches and the diameter of rod BC is 0.75 inches. We'll plug in both values to find the respective areas for each rod. That's going to be about 1.227 inches squared for rod AB and 0.442 inches squared for rod BC. We finally have all the values we need to solve the problem. We'll plug in the values for the areas into the stress equation for each rod. Notice that we now only have one variable in the equation, which is N sub A. We can rearrange the equation to get rid of the fractional form using some algebra. Then we can solve for N sub A to get 18.75 kips. That's great, but it's not quite what we need. We need P. Remember our equations of equilibrium? We determined that P equals N sub A minus 12. 18.75 minus 12 gives us our final answer, which is P equals 6.75 kips. We did it. We found our solution. If you'd like to see the second way to solve this problem, we'll do that now. It basically revolves around sectioning the rods differently so that we can solve for P directly instead of having to use N sub A. Again, we have our free body diagram. But this time, rather than sectioning from the top down, we'll section from the bottom up. That means we'll start by finding the internal resultant force in rod BC. We'll call that force F, and we can use our equations of equilibrium to find that it's equal to P. Then we'll find the internal resultant force in rod AB. When we section it, we'll consider the bottom half of the system. Again, N sub A acts upward, the 12 kip force downward, and P downward also. If we rearrange the equation, we'll see that N sub A equals P plus 12. Now we'll move on to the stresses. This time, the internal force in rod BC is P, and the internal force in rod AB is P plus 12. We can recall our values for the cross-sectional areas on the screen. We'll plug in the areas into the equation again. You can see that the only variable in the equation is P, so we can solve for P directly. After some algebra, we'll get the same solution. P equals 6.75 kips. That's great. I hope this two-part lecture and example series helped bridge the gap in your understanding of stress. If you have any questions about this topic, feel free to ask in the comments below. Thanks for watching.